Good afternoon. My name is Barabanova Irina, and I, with my colleagues Nikitin, Nikolay, and Vychuzhanin Pavel, would like to present sensitivity analysis of the composite data-driven pipelines in automated machine learning. Nowadays, most of the AutoML solutions solve an optimization problem for the model obtaining using different optimization algorithms, provide with ability to configure hyperparameters of models, and feature selection. However, software for solving real-world problems requires much more automation, which affects the quality assessment, machine learning problem identification, flexible architecture, and much more. The actuality of this research is dedicated by the necessity of quality improvement of the AutoML modeling results. We want to propose flexible methods of sensitivity analysis that can be applied to various machine learning pipelines. Such an approach can be used as a part of an AutoML to achieve a better quality of modeling, simplify the pipelines, and analyze its properties. For instance, SA could answer the following question: why a given operation block in the pipeline is located in a certain place on the graph. There are a lot of state-of-the-art sensitivity analysis methods that exist. The original goal of using sensitivity analysis is to uncover different sorts of uncertainties of black box models. However, it's generally applied to only a single model, for instance, to estimate the importance of its hyperparameters. But in the case of ML pipelines models, the structure of a final solution also could be examined via sensitivity analysis. Sensitivity analysis applications are already presented in machine learning. For instance, it allows one to discover the impact of various model architecture aspects on the prediction quality. That is especially actual for deep neural networks. The task of feature selection also refers to SA, since the features can be considered as parameters that affect the model output differently. Besides classical feature selection methods from ML, global sensitivity analysis methods can also be applied. Additionally, explainable IE methods can be noted as an alternative way to estimate the sensitivity of ML model parameters. For instance, SHARP and LIME frameworks should be highlighted as quite popular here. In the real-world applications of modern data science, the data-driven models for complex multi-scale processes can be represented as nonlinear pipelines that consist of different blocks. These pipelines can be named composite models and described as nodes and edges of the directed acyclic graph. The optimization problem that is solved during structural identification of such a graph can be written as presented on slides, where f is an objective function, composite model C that consists of set of various machine learning operations M with parameters P and directed links between them L, trained on the input data X. However, it can be necessary to analyze the results of the optimization from the structural point of view. There is a set of questions can be raised for any pipeline, including whether knowledge can be removed, changed, or added to the composite model to improve the prediction quality or simplify the structure. With the help of sensitivity analysis, there is an opportunity to assess the structure quickly and make sure it doesn't have redundant parts. Since AutoML provides solutions that can be represented as a sequence of known or unknown models, anyway, their interaction makes such a solution as a black box also. The structural sustainability estimation can be represented by the sustainability index, which considers the length of the original composite model and the number of redundant parts found via analysis, and have an equation as presented on slide. During analysis, a lot of samples with different structures of original composite model are generated and quality is compared. It's needed to notice that the procedure of SA is much cheaper compared to optimization algorithms. Using this index, we propose algorithms to allow reducing the complexity of pipelines by iteratively removing the least important operations. Multiple times analysis algorithm on the top of the slide indicates that the analysis is held every time after the worst node deletion found in the previous iteration. Such an approach points out the uniqueness of every composite model and believes that some partials could behave better or worse depending on the presence of others. The one-time analysis deletion presented at the bottom of the slide illustrates that models are independent and the most significant models for the current task will remain anyway. The decision about node redundancy is made based on the modification approaches, including node deletion and node replacement. So the corresponding indexes are proposed, where S is the sensitivity index of each block based on its removing or replacement, and Q is the quality score of the composite model. As a result, the experiments for classification and regression tasks were conducted using benchmark datasets. The results represent the comparison of sustainability indices of the automatic and random composite model design. The left table represents that in 4 classification cases out of 5, the sustainability index is lower or is better than the average index of the 3 random composite models. See the results in blue frames. There is one observation that in 2 cases out of 5, the analysis leads to approximately the same pipeline length, not depending on the approach. The names of these cases are in red frames. For regression cases, only a few composite models show sustainability. In most cases, random design models were more sustainable on average. Such contradictory results can be partly explained by some specificity of composing process used for experiments, lack of presets, using the only quality metric which may not fit the task, and etc. For the regression task, such analysis still has room to investigate. In addition, there are some experiments with analyzing the automatically built chains using some samples of the original task data to investigate whether the SI could reach the convergence for the task. In other words, if any similar solutions could be achieved. The results presented in table shows that in 3 cases of 5 different subsamples generate original composite model with approximately the same length. See the cells in the light green. These composite models differ from each other with no more than one node. Moreover, in 40% of automatically designed models, sensitivity analysis leads to the same length of composite models. See the results in bold. Even though the composite models gained from the 3rd subsample in the last task, see the red cell, has similar indices to the 3rd subsample, but has different original model length and the number of deleted nodes. The identical scores do not guarantee the convergence to the same composite model length in that studies. The analyzed pipeline is presented by the chain variable in the code snippet. The chain sensitivity analysis object conducts with different sorts of composite model modifications defined as approaches. There is more information about modification approaches available and inspiration for the custom application of structure analysis available in the official framework FIDO documentation. The obtained results is visualized as presented on the slide also. So in conclusion, we'd like to notice that application of presented sensitivity analysis algorithm for composite models allows to measure the importance of certain blocks of the pipeline. Also, it helps us to improve the resulting solutions via the identification of unimportant models or operations. And what is more, it can help to reduce the computation costs in the hyperparameters optimization of their pipelines, removing unimportant parameters for a given case. For further investigation, and one of the possible usages of the proposed assay methods could be a possible direction to improve the explainable AI methods from single models to the ML pipelines, or to help AutoML users to highlight bottlenecks of them manually created composite models. All the methods and algorithms described in the paper are implemented as part of the open source framework FIDO and available in the repository. Thank you for your attention.